I'll get to a function field soon. Let me just start with fields. And let me, in fact, start with existential first-order definitions, although we've seen them often enough. Let's just fix some notation. So I will always work in ambient structures which are fields. So given a field, maybe sometimes I will consider some subring, which doesn't necessarily have to be a field. Could be all of R. And if I then fix a natural number and some subset of f to the n, that we call existentially definable, essentially first order definable. Let me write this out only once over R. So from now on this will be just like this. Just save me some time. Yeah, let me just say it without writing it. If it's existentially definable in f as in the language of rings, doesn't matter if you allow a minus sign, and with coefficients or with parameters, I should say, from this subring R. And if I don't mention the subring R, I'll just take R equal to f, and you can allow other parameters all. Okay, so I don't write this down. Let me instead give you an equivalent definition. I'll use a more algebraic definition if I can find some other constants k and m, some polynomials over R, the coefficient is R, in n plus m variables, such that this set is precisely the projection of the zero set of this system. So. Keep the doors closed, maybe, or the windows. Yeah, so if you've never thought about fields, you might think that this is a more restrictive condition, because in the first order formula, maybe you also want to allow inequalities and disjunctions, but it turns out that if you restrict to fields, this really is the entire situation. Okay, and then I want to ask for a specific field, kind of what are the existentially definable subsets? The motivation might be that we want to kind of understand the complexity of a field, or how rich the information is contained in the theory of a field. And that one way to do this is to see how many, in a philosophical sense, not in the cardinality sense, subsets of this field are existentially definable, how rich they can look. Yeah, so given the field f, let me just take the case n equal to 1, which subsets are existentially definable. Yeah, so, yeah. Seen all of these, we take the complex numbers, then we get only finite and cofinite sets. Really, these are definable, but quantify elimination in algebraically closed fields if you want. These are the only definable sets, so complex numbers very boring. Take real numbers, and you get a little bit more definable sets, existentially definable. I say definable, but I'm only caring about this existentially definable throughout this talk. Although it's the same in the case of these two examples. We get finite unions of intervals. And if we take something like the rational numbers, well, we get a lot of existentially definable sets. So. Philosophy being, this field is easy, this field is also easy, but slightly less, this field is very hard. All of number theory, or maybe all of number theory is in this field. In fact, if I would ask you, can you give me a subset of Q which is not existentially definable, you might struggle, or at least to show that it's not existentially definable. Of course, most subsets of Q are not existentially definable, just by cardinality reasons, but it may as well be, as far as we know, that any recursively enumerable subset of Q is existentially definable. Maybe all recursively enumerable subsets. We don't know, this is still open. This completely reduces to one specific set. Namely, if I look at the integers as a subset of the rational numbers, is this existentially definable? clearly it's recursively enumerable, so if this thing up here is true, then it better be existentially definable, but in fact, if we can show that this is existentially definable, we get all the other recursively enumerable subsets for free, because it becomes bi-interpretable. Let's see where we know this result. Yeah, this we don't know. At the end of this talk, we still don't know. But it is, so we can say a lot, right? We can by hand just, to prove some set is existentially definable, we can just do by hand. And we do have many existentially definable subrings of Q. So if we fix a prime P, and we look at the following subring of Q, the localization at P. So again, to spell it out, it's those rational numbers where the denominator is not divisible by P after reducing. So this is a local subring of Q. It's a valuation ring. If you haven't figured out yet what the leitmotif of this day is, I think it's valuations. Just like in Franz Victor's talk, there's not a Hanselian valuation, there's many valuations on Q. Nevertheless, these are, so for any such prime number P, P is existentially definable. And this was already observed. Okay, let me write it down. By Julia Robinson around 1950. Now, I don't think she literally says this. I think she accidentally defines intersections of two such rings for two different primes, which is sufficient for the purpose that she wants to use this for. Essentially the same techniques. Can you define this ring or any finite intersectional set? And let me, so I think Björn mentioned this in the introductory school, but didn't discuss a proof. Let me actually give you a proof, at least for half of the primes. So if you take P prime, congruent to 3 mod 4, and I claim that the set can be described by the following existential formula. Take 3 extra parameters. It's precisely when 1 plus p minus 1 times p times x squared is represented by this quadratic form, y1 squared plus y2 squared plus p times y3 squared. Yeah, so clearly this is existentially definable. If I show the equality of these two sets, then I've shown that this is existentially definable. And something similar works for the other primes, but not this exact same formula. Okay, let me tell you how you could prove this. We must write this again. Just call this star. Maybe that starts. Yeah, so take some x. Then the property star. Okay, what does it say? So this specific formula really has my known parameters p and p minus 1 x in particular on one side, and here it's just saying it's represented by a quadratic form, so it's in the image of this quadratic polynomial. And we know it's a theorem from number theory that represented by a quadratic form is a purely local condition. So I'm saying this property star for some given x is equivalent for saying, rather than finding these y1, y2, y3 in Q, I find them independently everywhere locally. So I mean for every, so either in R or in every QQ, let's say. Yeah, there exist these y1, y2, y3. And then the same thing as there. Now it looks like I've replaced one problem by infinitely many. But then if you know a bit of number theory, then you can verify that all but one of these conditions actually trivialize. So for example, at R, clearly whatever x is, this is a positive number, it's a positive number plus a positive number, squares are positive, so it's always going to be some positive real number. And of course, I can always find the square root of a positive real number. And similarly, for all prime numbers, except maybe for q equal to p, you can show that this condition completely trivializes, holds for any choice of x. I mean, because I chose the coefficients correctly, so some work to be done. Then you show this is entirely equivalent to just having it in QP. Same equation. And then you do some mod p calculations or mod power of p, you use Hensel's lemma and so on. So this is some exercise in number theory to see that this really holds precisely when x lies in the valuation ring, when the p-adic valuation of x is non-negative, which is precisely saying x is in yeah, so this theorem I used here, this is the main thing the main reason why I wanted to give this. This is a theorem of Hausdorff. Johan also mentioned this already in his talk, I believe. Sorry, I didn't mention this in his talk this week. Yeah, this is an example of a local global principle. So for certain categories of varieties, to see whether they have a point, it suffices to check this everywhere locally. This is the main thing, and then I chose my coefficient carefully enough that it actually gives you exactly the local condition you want. Yeah. So every few months, I check whether ChatGPT knows how to do math, and then I check this, and then I'm reassured that my job is safe, at least for this reason. But I gave it this equation and said, what does it define? And it gave a completely correct proof. So this was to my surprise, I should say. So if you get stuck, then you know who to ask. Any questions so far about this? Let me move to function fields. What's that? Well, we get good training data, maybe.
You might be watching your talk.
What's that?
You might be watching your talk.
Yeah. Okay, so I don't actually want to talk about number fields, I want to talk about function fields. So I don't just mean global function fields, I want to start with any base field k, and then I want to form, let me first say, the rational function field, so a pure, a simple transcendental extension, so by definition, fractions of two polynomials, one variable. Yeah, so this is a rational function field. I won't say one variable, I'll just say rational function fields. And I also want to think about finite extensions maybe of such fields. Yeah, so finite extension thereof. Just call the function field in one variable. Well, these are in a way analogous to they are in a certain way analogous to number fields. Yeah, over Q and over any number field, you have some infinite collection of valuations, independent set valuations, different set valuations. When you take any specific element of Q, it has non-zero valuation at all of, but finitely many of these valuations. And similarly, on such a function field, rational function field, or a general function field in one variable, you have an natural infinite collection of valuations, namely those valuations which are trivial in the base fields. But any specific element has non-zero valuation at all, finitely many of them. And I want to ask, these occur naturally in geometry as the function fields of curves, this rational function field being the function field of the affine line, projective line. Yeah, and so the question I want to ask is, when are there existentially definable valuation rings? I'll just try this, but I mean these specific, non-trivial, of course, valuation rings, which come from smooth points on the curve in KT. Yeah, so everywhere I really care about general function fields in one variable, but all the examples and proofs I will give in this talk will be just for rational function fields for simplicity. Yeah, so specifically an example of such a valuation. Make this very clear. Yeah, so the degree valuation. On such rational function fields, let me just say the valuation ring. And that's all those valuations where all those functions is rational functions, yeah, where the degree of the denominator is bigger than or equal to the degree of the numerator. That's an example of a valuation ring on such function fields. Good. So let me mention an example due to Denef. Quite some time ago already. So he showed that
1478.
What's that?
1478.
Not that old.
Quite some time ago.
It's a degree valuation. Okay, so this degree valuation in the rational function field over R, the real number, is existentially definable, and you really just need coefficients in ZT. Let me give you a proof of this. I'm not giving Denef's original proof. I'm also not giving his original formula, but I'm repackaging the same ideas. I don't claim any originality for this.
And ChatGPT for this?
Well, I didn't use ChatGPT for this. I also came up with this proof for myself, just to be clear. Okay, so I can give you the formula right away. So I'm taking some arbitrary rational function, which I'm apparently calling u now, and my claim is that this u lies in this valuation ring, so can be written as a rational function where the numerator has degree no larger than the denominator, if and only if. And now let me give you the formula right away. There exists y and z, and f1, f2 in f. This is f. Such that, okay, let me not make a mistake. Y squared is z cubed minus 4. What's the other thing? This rational function is the sum of the two squares, f1 squared, f2 squared. Okay, let me again call these stars, so I don't have to rewrite these every time. So let me before we try to analyze this equivalence, just look a bit at what this right-hand side is really trying to say, what the content is. So note, let's look at these two equations separately. I mean, this here is the equation of some elliptic curve. Right? So y squared minus x cubed, or z cubed minus 4 defines an elliptic curve. And then it's a standard result that such an elliptic curve defined over the base field of some rational function field cannot have any non-constant points in RT. So, every RT point is an R point. Yeah, so you could see this from the von Hurwitz formula, but it's an even older result than this. So what this equation is really just saying, z doesn't appear here. This equation is really just ensuring that y is a real number, is a constant. Of course, for every real number y, one can find such a z. So that already covers this first equation. And the second equation is saying that some rational function is the sum of two squares in RT. And this too has a more intrinsic meaning. Which I will tell you. free to interrupt me. There may be more harmful mistakes than lines which look like 4s. So the second observation is that for some rational function f, to say that f is a sum of 2 squares is the same as saying that for every real number, f evaluated in t is non-negative. And so clearly, if you're a sum of 2 squares and you evaluate in some element, in some constant, you must get something non-negative. But this turns out to be equivalent. You only need 2 squares for this. Okay, technically, f is a rational function. It can have poles, so I cannot write this. So I mean, there may be finitely many elements I have to exclude. That's fine. So this equation over there, what I claim is equivalent to you having lying in this valuation is really equivalent to saying there exists some real number y such that for any real number t, u of t squared, t squared, divided by t squared plus u of t squared is at most y. You see, I mean, this is clearly a positive function. It's clearly, it cannot take negative values. For y minus this function to be a sum of 2 squares, so to not take non-negative values, we are asking that this function is uniformly bounded by some real number y. Okay, and now I claim that this holds precisely when u lies in this degree valuation ring. So let's look at the 2 possible cases. So, case 1, u lies in this valuation ring. Case 2, u doesn't lie in this valuation ring. Okay, so one verifies that if u lies, yeah, go ahead.
It's y minus?
Yeah, this is a minus sign, not a multiplication sign.
Ah, that explains.
Yeah, good that you ask. Y minus. Indeed. Yeah. So one verifies that, so just by computing the valuation, if u has non-negative valuation and the same holds for this rational function, t. Now the value of this will just be 2 times the value of this. So if it doesn't lie in the valuation ring, it's the same as this rational function doesn't lie there.
Is there a square missing? And then denominator there?
Here there should be a square. Yeah, it's the same function. Now, what do we remember from high school? How do we compute the limit at infinity of a rational function or of a rational function? Well, when is this limit? When does it converge at infinity? That's precisely when this limit. That's precisely when the degree of the numerator is not greater than the degree of the denominator. Yeah, precisely when this lies in this valuation. Okay, no, this should then be small t to be consistent. Lies in R, and here small s. You agree? Now observe that this function, regardless of what u is actually always defines a continuous function from R to R. So u squared. So the map from R to R, mapping e to this thing. Is continuous, which is maybe not immediately obvious. I'm claiming it cannot have any poles. It's defined on all of R, it doesn't have any poles. Right, u definitely might have poles, but then the numerator here and the denominator have the same order, so they cancel out. And there can also not be any new poles introduced, because here in this denominator we have a sum of two squares, which is always positive. So I'm claiming this is always the final all of R. So let's make a picture. So of this function, the graph of this function, u squared t squared over t squared plus u squared. So it must be the final all of R. In this case, it has a limit. So it must be, I don't know, something like this. In this case, it doesn't have a limit. It must be positive, so it must go to infinity. And we see that in this case, it's bounded uniformly, right? You use the definition of the limits, then you restrict to some bounded interval, and there it's a continuous functional and compact interval, so it must have a uniform upper bound. Right? So in this case, this condition holds. In this case, it doesn't. This concludes. Yeah, so in this first part, the elliptic curve had nothing to do with the real numbers. And this argument worked completely for any field. But here we clearly use the real numbers properties. Okay. So what about other base fields in R? Well, there are many specific cases where we know that that some valuation ring can be defined. I will give some overview of this. Let's first look at characteristic zero examples. So each time, K is the base field, and we think about function fields, general function fields maybe. Well, the results are sometimes proven in steps. Yes, here is the case. What did Denef originally prove? So his proof works for the real numbers, also works for the rational numbers. After some modification, I'm not saying the exact same formula, but one can also do this for rational numbers. In fact, for any real number fields, this a similar argument, small slight modifications works. So this was due to Denef, specifically for the case of rational function fields, and was then, so this was 1978, 1478, and then myriad, a lot of geometric machinery around 2005 to do this for general function fields. So when I say general, I mean of finite extensions of this, with an important caveat that you really can only define those valuation rings of which the residue field is also real. Right? So you could have a function field over R where all the places are complex, and then it doesn't work. Periodic function fields. One can also do this. One can in fact do this for all number fields, also the ones which don't have an embedding into R, as well as certain algebraic extensions of number field, essentially as long as they embed into some QP or some finite extension of QP. Here there's really quite some history. I don't want to say exactly what each author contributed to this, but also because it's sometimes a bit implicit in the works. I will come back to why it's often very implicit in the literature. But I guess the first who worked on this were Kim and Roche in around 95. At least in the case of rational function fields and alt P. Yeah, kind of very implicit. For general function fields, there was the same paper of myriad, and as I understand, it's kind of somewhat simultaneously by Kirsten Eisenträger. So for general F, also still for P greater than 2, this was around 2005. Yeah, same also over there.
Nicolas?
Yeah.
I don't think they define the valuation rings. They define parts of it.
Yeah, exactly. Yeah, it's a good point. I will, if it's okay for you, I'll come back to this in just 2 minutes.
Okay.
So indeed, so Just like a little bit like with the example of Robinson I gave, often the first people who find something in this direction don't explicitly obtain this existential definability with the valuation. Let me get back to why this is soon. But let me just mention de Grote and de Meijer. So this is Claudia de Grote with her PhD supervisor, Jeroen de Meijer, 2012, to cover rational function fields for p equal to 2. And then indeed, Russell Miller with Sasha Klappentoch explicitly cover general valuation, the definability of general valuation rings in function field, arbitrary function fields over number fields, as well as algebraic extensions, which can be embedded into some local fields. I should say something about the characteristic P case as well, and then I'll get back to why people care about this. Maybe I should use this white thingy, right?
It makes it better.
Yeah.
At least for us.
Well, but now if you cannot read it, I cannot blame it on the water, right? Okay, so these are a list of characteristics 0 examples and characteristic P. The first examples are due to about finite fields, well, not just P, powers of finite fields, due to the late Daans, around 91, and pop characteristic, and Carlos Videla, and even characteristic.
What about Romney? He precedes Daans.
What's that?
Romney.
I didn't catch it.
Robert Romney.
Romney.
Right,
yeah, of course. This was much, when was it?
much earlier.
80
something.
80 something. 80s. Yeah. We'll cover rational function fields as well. Over finite fields, crucially. Yeah, so these are the global function fields. And then there were a sequence of work. So Fred and Roche also very briefly afterwards considered certain also rational function fields over certain base fields, which are not finite. In 92. And then this was in subsequent papers by several non-empty subsets of Kixen-Eisenträger and generalized to arbitrary function fields, which are not necessarily finite and not necessarily rational, but also larger base fields. Let me just mention the conclusion that, so this is Eisenträger-Klappentoch, 2017. That you can work with arbitrary function fields over field K, which is some algebraic extension, some algebraic, non-algebraically closed, yeah, non-algebraically closed extension of a finite field. An arbitrary function field in one variable. Okay. So there are a few questions which come up naturally, I think. One is what unites all these examples, all these specific cases, but maybe more importantly at this point, why do people care? So the motivation of this problem comes from the built-with problem, so undecidability questions. Undecidability of existential theories. As we saw mightily on Tuesday. So, and this was the motivation of not all, but many of the papers which I mentioned here, especially always the first one, often the first one in a sequence. And since this was their goal, they don't always precisely state the maximal conclusions under the minimal hypotheses. That's why it's sometimes a bit hard. Indeed, Kim and Roach in their papers, they care about this Hilbertson problem, just like Daans does, and whether they exactly obtain this existential definability of this valuation ring is maybe a bit subjective. So what's, let me say, the version of this, not the most optimal version, but a version of this relationship. So this version, just for rational function fields, let me say this, is due to Denef in characteristic 0, Degas in Sidela in positive characteristic. If you have such a field, yeah, so I'm stating it just for the rational function field. And if you have some valuation ring, let me take just this valuation. So assume that this valuation ring is existentially definable. Yeah, now I have to be precise over R, where R is some, over RT, let's say, for some computable subring. R of K. Yeah, I have to restrict the language to something computable for this to make sense. Then, let me not be super precise about this, it's just a motivation. Hilbert's 10th problem over F with coefficients in RT is undecidable. So this was the original motivation of the Denef, as well as Daans and Videla in RT is undecidable. And there are versions of this also for arbitrary function fields. They're significantly more involved. Yeah, so in the characteristic 0 case, essentially Moret-Bailly figured out, and the positive characteristic cases, Eisentrager and Schwab talk about. So this is the motivation for thinking about existential definability of valuations. I kind of want to postpone this a bit, since I think the problem is nice on its own. But the other question is still there. What about general base fields? What do all these specific examples have in common, or not? So what about general K? So the case where the base field is algebraically closed seems to be genuinely really hard, especially in characteristic zeros. I don't have a proof for this that this is hard, but these fields they are chronologically trivial. There is somehow very little room to define anything meaningful in their function fields, and we have no idea. Thomas Cameron, he doesn't seem to be here today, but he's thought mightily about variations of this problem. I don't think he's solved it yet. Okay, so what about K not algebraically closed? The complement of it. So, yeah, let's switch. So here, together with, at the time, my PhD supervisors, Karim Becher and Philip Wittmann, we were able to show something. Let me state again the rational function field version of this, and then maybe also otherwise not be completely optimal with the hypothesis. So assume you have some large field K, we call it this. Let's take characteristic differential from simplicity. We also cover characteristic 2, but just giving an example here. Let's assume we have some element in K whose square root doesn't lie in K. So clearly this implies K to be not algebraically closed, but it's very close to asking just this. Yeah, and let's just consider this rational function field over K. Then this valuation ring is existentially definable, and you don't need more coefficients than just a witness of this non-algebraic closeness. Just coefficients in Z sets. Make some more space. And meanwhile, comment on some things which I won't write out. So in characteristic 2, we also proved this. Somehow we work with separable quadratic extensions. So instead of taking some C whose square root doesn't lie in K, we somehow need to take the coefficients of an irreducible polynomial, of a separable irreducible polynomial of degree 2. That's the only thing that changes. So we need kind of this witness of this having a quadratic extension. This quadratic extension may seem a bit arbitrary. It comes from the fact that we work with quadratic forms. So I'm confident this is not a meaningful restriction. So we can definitely generalize these arguments to assuming that K is not algebraically closed, and you just need in the coefficient some witness of this non-algebraic closeness. But this large is a more interesting restriction. Should I write this down? We've seen it many times, so I'm not sure anyone wrote it down, what large means. So it means that every smooth curve over the base field either doesn't have any rational points or has infinitely many. Is it okay if I leave it at this? So let me give some examples of large fields and also some examples of non-large fields. For those not so familiar with this, keep the theorem there. So algebraically closed fields are large, but they're not useful in this theorem. Real closed fields are large. Periodically closed fields are large. Any Henselian, non-trivial I should say, of course, Henselian valued fields are always large. Complete topological fields, separately closed fields. AC fields, and so many fields which come up naturally. But also many fields are non-large. In particular, this contains all number fields. All fields which are themselves function fields, so you can get a base field which is itself a function field, of course, and all finite fields. If I would take some infinite algebraic extension of a finite field, that would be large again. So, interesting tension there. Yeah, so this theorem covers, I've now wiped many of the historical examples. It covers some of them, but certainly not all of them, right? Not all the number field examples, for example. It also covers some new examples. Yeah, so just to motivate us, so just to give some new example, you could have a base field K which contains an algebraically closed subfield, but it's not algebraically closed itself, and none of the things which I mentioned before would be applicable in this case. But so you could take Laurent series field over C, for example. But still, maybe I should not use T. It's whatever. Let me just give one example.
By new examples, you mean new examples for definable existential?
Yeah, not of large fields, yeah. Thanks for clarifying. So this is definitely not a new example of a large field. I don't claim to have any new examples of large fields. It's an example where this theorem is applicable and which didn't follow in any straightforward way, at least not in the way I could tell from results in the literature. But yeah, many remaining, so first of all, this doesn't even unite the existing cases we know, and it also leaves many cases open. So, what if K is itself a function field? Or a more number theoretic setting, we can look at fields K, which come as an algebraic extension of Q, but which are far away from being embeddable into a local field, but which are also not yet algebraically closed. And these really do come up in number theory. So you could look at the base field, which is, for example, the abelian closure of Q. So you take the union of all Galois extensions of Q within some algebraic closure. This gives you a non-algebraically closed field, of course, which is of cohomological dimension 1, so it's far away from locally embedding into a local field. Yeah, so for these base fields, and maybe they are large. This is a large field, but we don't know. But let's assume it's not a large field, then how do we cover this? Good. Any questions so far about statements or examples? Yes, go ahead.
Is there an example of field where we know that the O degree is not definable?
That's a good question. No. I mean, maybe there is, but I don't know. We don't know. Yeah, like I said, somehow the algebraically closed base field seems to be the hardest field because you have the least expressive power. Yeah, I don't know. I don't think there is a reason for why this should not be existentially defined. So let me fill out 8 minutes or something to give you some key ideas on about how this would be proven. To call this a proof sketch would be giving it too much credit, I think. Let me say proof by analogy. So I specifically set up this proof of this theorem of Denef. Instead, it's not how he proved it, so I could now prove this theorem in a very similar way. So we start by proving this theorem over there. Yeah, we define f, take some u in f. I can give you the formula, or almost give you the formula. So I claim this u lies in this valuation ring. Even only if, let's see if I get it correctly, there exists y in k, and f1, f2 in f, such that y minus, let me write this and then see what I have to add some exponents. I should use the c here. Minus c times u squared, so the denominator is t squared minus c times u squared. And here I'm putting minus c times f2 squared. Yeah, so remember this c was just some witness of non-quadratic closeness. It was an arbitrary non-square element. Before we were thinking of the field R. What's an example of a non-square in R? It's minus 1. So if you plug in c minus 1, we get here again the sum of two squares, and we get the sum of two squares in this denominator again. So this really specializes almost entirely, should be square here, to the example I gave before. This rational function looks a bit differently, but it's quite similar. Yeah, so I should then remark that just assuming k is large, k is existentially definable in f, observed by Jochen more than 20 years ago, I think, by now. 2002 or something. Yeah, so can I say it's essentially the same trick as before with the curves, but you have to do a bit more. So it's a bit more tricky, but the same ideas go into it. Let me say it like this. But you have to use this largeness condition in some clever way. Yeah. So if I admit this remark, then I can quantify existentially over k and obtain some existential definition of the base field. Yeah. So how would I prove this equivalence? So I'm claiming that the equation from right to left, you start from some representation. This is elementary. I'm not saying it's easy, but it's elementary. This doesn't assume that k is large. This does not assume k large. Yeah, you just write down this thing and you compute the valuations on the left side and on the right side. You see they don't match. if you don't like the valuation ring. But for this other direction, how would we begin? So before I used this topology on the real numbers to kind of characterize those elements which were represented as the sum of two squares in this rational function field. So now I want to characterize those elements which are f1 squared minus c times f2 squared. But how would I mimic this boundedness argument? So how would this go? Here is where the by analogy part is going to come in. Yeah, so let's look at the special case. Where the base field is actually a power series field. Field of Laurent series over different fields. People who have worked with large field before will not be surprised by the special case. Okay, so this naturally comes with a valuation, this S-static valuation. And I now want to look at the set, call it V, of formally I should say equivalence classes of valuations W on F, which are an extension of the S-static valuation. So I should say, if I take this valuation, I restrict it to K, I get precisely this S valuation of the base field. Yeah, so I can look at this set. I claim that I can endow this V naturally carries a compact topology. Actually, let me tweak this V slightly. No, I want to define some continuous function as before. I associated this rational function. Before I was only looking at real points, and now I somehow only want to look at the corresponding thing. Real points, that's the points in RT where -1 is not locally a square. So let me now only restrict to those valuations where C is not locally a square. This is the initialization. And I claim that this naturally carries a compact topology. I see that I'm slightly out of time, so I will say somehow, this thing, where is my rational function, this thing over here, defines a continuous function of this. And I can kind of find some common upper bound. So find some maximum. And then, similar to the proof I gave very much in the beginning of with this Hasse-Minkowski theorem, this solvability being completely encoded in local data, one also has such a thing for function fields over complete discretely valued fields. Yeah, so this is local global principle. There exist many versions. Let me give a version to Nicolas Daans, Parimala, and Suresh. From 2012, saying that, well, if Q is some periodic form, over this function field, in this specific case, let's say in at least two variables, and if we take some element of F, then Q represents this element if and only if it does so everywhere locally. It does so over the initialization for all valuations W, which extends this S-static valuation on the base fields. Yeah, so by this analogy, and one has to do some work, I'm not saying it's easy at this point, one carries over One does a similar argument as for the case of real numbers. It works over this space fields. And then you think I just did some one special case, but there is this interesting characterization of large fields, which is the only thing we use, that if k is large, so k is large, if and only if passing from k to the Laurent series field over k is some existentially closed extension. So you don't add any solutions of equations. And this passes over to the rational function field. So maybe you prove this equivalence of the application from right to left just for this kind of base fields, and a posteriori the result falls out for arbitrary large base fields. That's just a characterization of large fields. I think that's actually also how this is proven, by just first doing it for these Hansinian valued fields and then carrying it over. I think I'll stop there. Thank you.